So this takes us to the keynote address as part of the Leo Gerard lecture series on workplace and labor studies. Dr. Han will be presenting on an overview of key respiratory hazards in mining and occupational hygiene lens. So Dr. Han is an associate professor with the School of Occupational and Public Health at TMU or at Toronto Metropolitan University. He has a BSc from McMaster University, a BASc from what was formerly Ryerson University, and an MSc from McGill University. He obtained his PhD in occupational and environmental hygiene from the University of British Columbia. He is certified in occupational health and safety, possessing both the CIH and CRSP designations. Prior to his academic appointment, Dr. Han was an occupational health and safety practitioner in a variety of sectors and overall has nearly 25 years of work experience. His general research interests are occupational exposure assessments, risk assessments, and evaluation of intervention to prevent occupational exposures. Please join me in welcoming Dr. Han this morning.
Now, great. Well, thank you very much again, Dr. Goggins, for the warm welcome. I'm very happy to be here and happy to share my thoughts about some of the respiratory hazards that are common in mining. So before we begin, I just want to explain that provide a disclaimer that the views and opinions are my own and not that of my employer, and I am going to be receiving an honorarium from Krosh to deliver this presentation. So just a quick background as to my education and experience. Um, as Dr. Goggins mentioned, I am formally trained in occupational hygiene. I have a Master's of Science from McGill University, and I also did my PhD in occupational hygiene. I do possess the Canadian Registered Safety Professional as well as a certified hygienist, and I've been involved in occupational hygiene since 1998. In terms of the research interest, Dr. Goggins already summarized that. If you're interested, once you get the slide deck, you can take a look at some of the publications that I have been a part of through the Google Scholar link. And then more specifically, I just want to highlight some of the work that I've done with mining. I'm sure some of you in attendance today have a lot more experience in mining, um, but I just want to share with you some of the stuff that I've done in the past. I was a working group member for one of the international standards, the ISO 23875, which is looking at air quality controls for operating enclosures, performance requirements, and test methods. And basically, this is to ensure that the environment where the cab operator is in is suitable and safe for the occupancy. I also published co-authored work with some colleagues that were working a mine up north, and where we looked at an engineering control to reduce the airborne exposure to particulates. And then I also supervised a student who was working at that one of the mines, and we looked at um, a novel exhaust system modification to reduce the asbestos particulate exposure. So when I was approached by Dr. Sandra Dorman about the topic for today, um, we had discussed a variety of different things. Given my background in occupational hygiene, she felt that this would be something of interest um, because I'm not sure how many people do too much occupational hygiene work. And so this was also a good segue for some of the other topics that were going to be discussed later on today. So the purpose of this session today is to give you an idea of some of the issues related to respiratory hazards from an occupational hygiene lens. We are going to first talk about some foundational occupational hygiene concepts, and then I'm going to focus on three key respiratory hazards that are found in mining. First one being silica, the second one being diesel particulate matter or DPM, and then the third being radon. And for each one of these, I'm going to go through some of the different sources of these hazards and their health effects, how we go about conducting occupational hygiene exposure assessments, talk about the associated occupational exposure limits or OELs, and I'll explain more what that concept means, and then provide a brief overview of some of the literature surrounding some of the exposure values and the associated risks. And then the last thing I'll cover is some novel exposure judgment tools that are currently being used in the occupational hygiene realm. And basically, it's there to help individuals to assist with interpretation of exposure data. And I'll provide some more uh, information later on. And then lastly, we'll have Q&A. So the whole point of this is to hopefully raise your awareness of some of the occupational hygiene hazards. And the next time you go on site to mine, or next time you have any sort of discussions or consultation with individuals that do work in mine, hopefully you keep in the back of your mind some of these occupational health hazards, because as you well know, a lot of these things are not in isolation. So you may be going there for an ergonomic assessment, but again, those occupational hazards are also present in the workplace. Okay. So I'm going to start off with explaining some foundational occupational hygiene concepts. Again, I'm not sure what everyone's background or experience is in occupational hygiene, so I thought it'd be good to provide an overview of some of the more foundational concepts. This is by no means giving you, allowing you to be an expert whatsoever, but just some of the terms and some of the ways that we go about sampling for some of these airborne hazards. Okay, so first off, what is occupational hygiene? According to the AIJ, the formal definition is the science and art devoted to the anticipation, recognition, evaluation, and control of those environmental factors or stresses arising in or from the workplace, which may cause sickness, impaired health, and well-being or significant discomfort among workers or among citizens of the community. The other term you might hear is industrial hygiene, sorry, but it's a bit more of a dated term, so we generally try to use the more modern term of occupational hygiene. And the goal of occupational hygiene is essentially to prevent occupational illness or disease. This is different from safety, which is more concerned about preventing of injuries or property damage. So we're looking at these long-term health effects that people may experience as a result of occupational exposure. Okay. So going back to those four key principles, I just want to give you an idea as to what they mean. So anticipation essentially is where you try to be aware of some of these occupational health issues before they arise. So let's say you are looking at a plant that's being built. You will look at the blueprints and get a sense of where equipment might be, where people might be situated, and seeing whether or not there's a possibility of exposure to the equipment or some of the hazards associated with a certain process. You might be reviewing new equipment that you plan to bring in. So you're thinking, how loud is it? Do people have to um, um, input something into that piece of equipment in order to generate, let's say, the finished product? So if they have to handle raw material. Okay. The next thing is recognition. And so this is where you would be identifying potential health hazards that already exist as a result of a process or task. So this is where you would be walking through a workplace that's in operation, and you would identify a variety of different potential issues. So let's say you see a worker, again, manually handling something, whether or not that's a toxic chemical, so that would tell you that there's a potential exposure there. You might think about the noise that's associated with that plant and determine whether or not that might be a potential risk as well. Okay. The next one is evaluation, and this is where we are trying to determine what hazard might be present in the workplace as well as how much is present. And essentially what you're trying to do is identify the hazard, if there is one in the workplace environment, and if there is one, how much is present, because you want to know whether or not that poses a risk to the workers. And so this is essentially done by performing a hazard assessment. Yeah. And then the last thing we talk about in the principles of occupational hygiene is control. We generally follow what's known as the hierarchy of controls, where you start at the very top, the most effective control being elimination, and then you work your way down the hierarchy. So the next step would be substitution if you can't eliminate, and then keep on going down to engineering, administrative, and PPE. This is not done in isolation. You might do it in combination, but the fact is that you start with the most effective and then work your way down to the least effective. For the purpose of this particular talk, we will focus mainly on evaluation, so how we go about performing exposure assessments. And the reasons for evaluation, there are a variety of different ones. So I just wanted to share with you why we go about doing exposure assessment. So the term you might hear, besides exposure assessment, it could be exposure monitoring, it could be hygiene assessment, air sampling, hygiene sampling. So all these are synonymous terms in the world of occupational hygiene. So why do we go about performing an exposure assessment? So the first one is to identify and determine an amount. I talked about that already. So you want to know what might be present and how much of that is present. The second one, and the most common one, is to determine whether or not the worker's exposure is in compliance with the legislated occupational exposure limits. And I'll talk about that later on in the upcoming slides. The third is that there may be instances where individuals have complained about a certain health effect, but you're not sure what's causing it. So you might sample the air to determine what might be present in the workplace air that might be resulting in these health effects. Number four is to evaluate the effectiveness of control measures. And essentially, what you're doing is that you're doing an air sampling before you implement control measures. Then you implement the control measure, and then you would sample after the control measure is in place. And you want to see that there's a reduction in the airborne concentration, hopefully lessen the exposure limits, and therefore you know that that exposure control is effective. And then the last thing is that we conduct exposure assessment for research purposes. For instance, in order to develop these occupational exposure limits, you need to know what people are generally exposed to. For epidemiological purposes as well, you want to know what concentration might lead to a health effect. Okay, so I already mentioned about the importance of occupational exposure limits. I just want to explain how this concept works. Essentially, it is the maximum concentration of an airborne substance that a worker can be exposed to over a period of time without the likelihood of experiencing adverse health effects. Essentially, it's a level of acceptable exposure. So, assuming that the occupational exposure limit of a chemical is 10 parts per million or ppm, if you measure that the worker's exposure was found to be 6.8 ppm, because it's less than 10 ppm, their exposure is considered acceptable. Conversely, if the worker's exposure turns out to be 13.2 ppm, and this is greater than the 10 ppm, then their exposure is considered acceptable. I just want to point out that doesn't mean that they will develop health effects with 100% certainty. It just means that they have a greater likelihood of developing health effects. In order to find the various OELs, in Ontario is found in Ontario Regulation 833, which is the control of exposure to biological or chemical agents. So there's a hyperlink for you to take a look at those things. What's important to note is that I'm sure many of you are aware, health and safety legislation is governed at the provincial level here in Canada. And so that means that there are different OELs for different jurisdictions. So if you are visiting a site or working at a site that is not within Ontario, you would have to go review the occupational exposure limits for that particular jurisdiction. Okay. This is an important slide in the sense that you're trying to understand the different categories of occupational exposure limits. I mentioned in the previous slide that it's based on a period of time. And then the different categories of occupational exposure limits are stratified by the time associated with it. So the first one is a time-weighted average, or TWA. And so this is a time-weighted average concentration for a typical 8-hour workday or 40-hour work week, to which nearly all workers may be repeatedly exposed without the likelihood of experiencing adverse health effects. Okay. The next one is a short-term exposure limit, or STEL, S-T-E-L. And so this is a 15-minute period. So TW is 8 hours, STEL is a 15-minute period. So this should not be exceeded at any time during the workday, even if the 8-hour TWA is within the exposure limit. Okay. And then the last one is ceiling, or C, or CEL. Sometimes you might see that. And basically, this is the maximum concentration that should never be exceeded. So the time associated with this is zero. So 0 seconds, 0 minutes, whatever you want to call that. Okay. So the bottom figure there kind of gives you an idea as to how these three are related. So the very bottom dashed line is the TWA or time weighted average. And you can see that there's peaks and valleys on this graph. And that's typical of a worker's daily exposure for the most part, is that it's not a steady state. It does fluctuate over time. And so that's why we call it time weighted average, because you want to average the exposure over this 8 hour period. The STEL, which is the middle dotted line there, and you can see the vertical lines, which tell you that that's a 15-minute period. So what you're trying to do is average the exposure over that 15-minute period, and then you're comparing that worker's exposure to a STEL. An example of a 15-minute task would be something like placing material into an acid bath, name as the name implies. It's a vat of acid, which is used to clean these materials or digest the materials. And so it takes about 15 minutes to load it, and then you can close it afterwards, and then it would do its job in terms of trying to clean or digest, and then you would open it up and it takes 15 minutes to empty out that acid bath. So that would be an example that I provide typically as something that is a 15-minute task or so. And then the last thing is the ceiling. And as you can see here at the top dotted line, that's the highest exposure for all these peaks that you see on the graph. And so you would compare that concentration to the associated occupational exposure limit ceiling to see whether or not the worker is considered overexposed. Okay, so typically we look at the time weighted average. So if you go back to that regulation 833 I showed you in the previous slide, um, most chemicals have an OEL TWA associated with that. Some might have a STEL, some might have a ceiling, but for the vast majority of chemicals are listed in the regulation, they would have an associated OEL time weighted average. Okay. In terms of the different occupational health hazards, typically the ones we're looking at that are within the purview of occupational hygienists are chemical hazards. So, like solvents or acids. Then you've got biological hazards like mold, fungi, viruses, sorry. And then last thing are physical agent hazards. These are sources of energy that could be harmful to one's health. So you're looking at noise, radiation, and thermal stress. The one we typically look at from an occupational hygiene perspective in terms of historical and traditional has been chemical hazards. And the reason for this is that chemicals have been around for a long time. There's also established sampling methods, which I'll talk about very shortly. And so when there's a chemical hazard in the workplace, you generally think about contacting an occupational hygienist for some consultation as to how to go about doing the exposure assessment. Okay. So in terms of airborne chemical hazards, um, inhalation is the most common route of exposure, not necessarily the most important, but the most common because as humans, we need oxygen to oxygenate our blood. And so we all have to breathe as part of our, in order to survive. And the main organ that's impacted is the respiratory system. Okay. In terms of occupational hygiene, we further classify airborne hazards into two general categories, one being particulates and the second one being gases and vapors. Okay. And the reason why we separate this out is that there's typically different sampling media required to sample a particulate versus a gas vapor, and I'll show you that in the next slide. And also the concentration units used to report these airborne contaminants varies. Milligrams per cubic meter is used for particulates, whereas ppm or parts per million is used for gases and vapors. So here is a table which shows you the general differences between particulates versus gas and vapors from a toxicological as well as an occupational hygiene perspective. So on the left-hand side, we've got particulates. On the right-hand side, we've got the gases and vapors. Okay. So we'll start with particulates on the left-hand side. You can see we're talking about metals, wood, silica, and it's typically generated by sanding, grinding, or cutting. And in terms of their size, you're looking at 0.1 to 10 microns. In terms of where they are deposited in the respiratory system, it really depends on the particle size. And of most concern from a toxicological perspective is the respirable fraction. So we'll look at the different fractions that are um, used in occupational hygiene. You've got the inhalable, thoracic, and the particulate. So the image and then the text go hand in hand. So the inhalable particulates are particulates deposit anywhere in the respiratory system. So these are typically larger particles. Then the thoracic is anywhere within the lung airways in the gas exchange region. And then the bottom, the respirable particulates are anywhere they're deposited within the gas exchange or alveolar region. So this is the most important from a toxicological perspective because if the alveoli are damaged, that can impact your ability to get oxygen into your blood. Okay. Okay, so then going back to this table, what we see here is that in terms of the sampling media, for integrated air sampling or traditional air sampling, which I'll talk about a bit more, we typically use a filter. So what's happening is that the particulates are trapped on the filter, and then from there you send the filter off to a lab for analysis. So moving on to gases and vapors on the right-hand side, gases are those that are typically in gas form at a room temperature. So that includes hydrogen sulfide and NOx's. And then vapors are usually liquid state, could be solid state in at room temperature. So some common examples here are benzene and ammonia. So how they become airborne? They're off-gassing. So when you buy furniture, new furniture, there might be a smell associated with that. So that's off-gassing. You can also it could also be volatilized if the temperature is warm enough. Okay. In terms of relative size, they range from 0.25 to zero point 0.6 nanometers, so substantially smaller. So sometimes for particulates, they are visible to the naked eye, but gases and vapors are typically are not. Okay. In terms of deposition in the respiratory system, it all depends on the solubility of that gas or vapor. And then the sampling media used in terms of traditional air sampling, we would use what's known as a sorbent tube. So a sorbent tube is a glass tube, and inside the glass tube contains a variety of agents in there. Typically is either charcoal or silica. It could be other type of media in there as well. But silica and charcoal are the most common ones. And what's happening is that the gas or vapor is adsorbed onto that tube and then you would send that tube off for analysis as well to quantify your gas or vapor. Okay, so I mentioned already that chemical hazards are within the purview of occupational hygiene and it's long-standing. And it's because we have a lot of methods associated with this in terms of how to go about sampling for these chemical hazards. So the two main sampling methods or agencies that develop sampling methods, sorry, in North America is the National Institute for Occupational Safety and Health, or NIOSH, and the other agency is Occupational Health and Safety Administration, or OSHA. So these are hyperlinks that take you to their sampling websites. And so basically all you do is look up the chemical of interest, and then you would find the corresponding sampling method. Now, there are hundreds and thousands of chemicals out there, and there may not be an NIOSH or OSHA method. So other sampling methods are available that you can consider. The Environmental Protection Agency in the US, the Health and Safety Executive in the UK. And as an academic, I typically look for these sampling methods in scientific articles. Okay. So if you are familiar with how to go about sampling for chemical hazards, you will have the background to know how to sample for biological as well as physical agent hazards. We just don't have time to cover that off. But once you have the foundation for sampling for chemical hazards, you should have some knowledge as to how to go about sampling for the other types of hazards. Having said that, the media will be different as well as some other nuances associated with sampling those other hazards. Okay. So how do we go about sampling for airborne chemical hazards? There are four different ways, and I'll break them down for you in the upcoming slides. But basically, You can use integrated air sampling, which is the traditional way of sampling in terms of occupational hygiene. You can do what's also known as grab sampling. This is typically for gases and vapors. Grab sampling is very short periods of time. There's also passive sampling, and this only applies to gases and vapors. And lastly, there are direct reading instruments. So I'll go through these in the upcoming slides. So for integrated air sampling or traditional air sampling, what this is essentially that you have a battery operated pump with a sampling media attached, and then you're drawing air using the pump onto that media. Okay. And then what's important to note is that in order to detect anything on that media, you must ensure that you sample at least the minimum volume, but you don't exceed the maximum volume. And you look at those sampling methods I told you about earlier, the NIOSH or OSHA methods, which will give you an idea as to what is the minimum volume allowed and what's the maximum volume. So that's one of the reasons why chemical sampling is using integrated air sampling. You have to refer to these sampling methods because it gives you all of this information. Okay. So in terms of integrated air sampling, you're using what's known as a sampling train. So these are the different components that you require for air sampling. There are three minimum components. The first is sampling media. As I mentioned, this is what is used to collect the air contaminants. So that could either be a filter or the sorbent tubes. You need flexible tubing, which is essentially connecting the pump to the sampling media. And the most common example of flexible tubing is Tygon tubing. And then we also have that air sampling pump. And most important thing about the pump is that you have to make sure it can sample at the flow rate indicated according to the sampling method. Some flow rates are ranged from 2 to 4 liters a minute. Some flow rates are a bit lower, zero point 0.5 liters a minute, let's say, for example. You just have to make sure your pump is capable of meeting the flow rate that's established in these sampling methods. On your right is an image of a person wearing a sampling train for the purposes of personal exposure measurements. So you see here that they've got a pump, here's the flexible tubing, and then this is the media. And it's circled here because the media has to be within what's known as the worker's breathing zone, which is about a 30 centimeter radius around the person's face, so that you're basically trying to get a sense of what they're breathing into their respiratory system. Grab sampling, typically for gas and vapors that cannot adsorb onto the sorbent media that we talked about, or they're non-reactive and non-absorbing. So some examples are methane, carbon monoxide, and nitrous oxide. And two of the most common grab sampling methods you can see here are the canisters and evacuated bottles on the right-hand side, those images, and then you get sampling bags as well. So these are very short durations, typically only a few minutes, and then you would send that off to the lab for analysis. The next one is passive sampling. And so this is for gases and vapors only. And essentially it works by diffusion. And the gas and vapor diffuse onto a permeable membrane. And the benefits of using passive sampling is that you do not need an air sampling pump. Okay, so there's no need for getting tangled with tubing. The weight of the pump can be bothersome to some people. You just have to clip this on to the worker's lapel, and then they can continue doing what they normally do. Um, in terms of determining the concentration, it might be a color change, or more typically, you send it off to your lab for analysis. Because it works by diffusion, these devices are subject to environmental conditions. So if you're in a very windy workplace, you might get inaccurate results, and also humidity. If the membrane gets wet, then you're going to be in trouble and you might get inaccurate results as well. This is typically used for time-weighted average exposure concentrations as opposed to STEL, and definitely not for sealing because we talked about the minimum volume you need to sample for. There's no way that you can get enough in a very short period of time in order to compare to the STEL and the sealing. So this is typically reserved for time-weighted average concentration measurements. Okay. What's important to note is that once you remove the cap and expose the membrane, you need to record the time that it has been exposed. So the start and stop time, you send it off to lab. Otherwise, you will not be able to get a concentration result. And then the last thing are direct reading instruments or DRIs. And the beauty of these instruments is that they combine both the sampling and analytical functions. All the other methods I mentioned previously, you have to send it off to lab for analysis, whereas DRIs, you don't need it. You don't need to send it off to laboratory. So this means that you get near real-time results and you can make decisions about the worker's exposure basically on the spot. Um, these instruments typically have data logging capability, so they record over time. That allows you to generate graphs. And I showed you earlier about the peaks and valleys. You can know what's the maximum exposure concentration for that worker, and then you can compare that to the ceiling limit. Okay. The other thing you can do is that you can set up a video, and then you can have these direct reading instruments along with the video recording of the worker doing their tasks. And then you can explain at what point in time or what task they're performing might be leading to greater exposure compared to other times of the day. Okay. And there are a variety of different direct reading instruments available. What's important is that you have to select it properly because not all instruments are designed in the same way. And some other thing is that if you are doing compliance testing, be aware that using DRIs may not be approved for compliance testing, so you may have to go back to traditional air sampling methods. Okay. So that's a quick overview of hygiene. I'm going to take a break here just to make sure that everyone has a chance to digest some of the material before we go on to the specific hazards that are associated with mining. So if there's any questions, I'll be happy to take them.
Does anybody have any questions up until this point? I have a couple of questions.
Sure.
Is that okay?
Yes, of course.
Okay, so I am so curious about this, like the ceiling limits. So with
Hmm.
these sampling devices, are they, with the advances in technology, are they measuring that automatically? Is there methods for alarming systems that are doing that in a workplace so that the person knows prior to, or like I know the traditional air sampling is the longer term, but I'm just wondering with the ceiling limit and the other limit you spoke about, just the 15-minute one,
Hmm.
are the devices actually designed to do that, to like to give you those quickly so that the worker knows they're in a dangerous situation?
Right. So that's a very good question. The ones that for the ceiling limit, oh, can you hear me?
I can, yeah.
Okay, sorry,
Mhm.
I can't see it. You could, okay. So in terms of the ceiling, that's a very good question. In terms of the ceiling limit, there are single gas monitors which have an alarm setting on that so that you can know whether or not you're close to reaching that maximum concentration. So it has both an audible alarm as well as a vibration alarm, which warns you that you are at the ceiling limit so that you can take measures to move away from the source or to leave the space for a little bit. So,
Okay. And so that's just for that's for, like you said, just
yeah.
gas. That's
Yeah, it's just
the,
for gas and vapors. Yeah, I don't know about ceiling, about the STEL, about those instruments, if they are able to generate a STEL on the spot, because I haven't used these instruments in a while for exposure assessment purposes. We're, as an
that's fair.
academic, you're doing research purposes. So I'm not
Yep.
100% sure if it can do still. I know for sealing it can be done.
Okay,
Yeah.
awesome. And so Judith's saying here there are a couple instruments. I know, so Judith does work, do air sampling very regularly. That's
Hmm.
so she does have, says there are some that have an alarm now. Thanks.
Hmm.
So I have another question too about the particulate size fraction. So with the inhalable thoracic or respirable particulate,
Hmm.
is there one that's considered more dangerous for, is there one type of exposure that's considered more dangerous,
Yeah.
or are they all equally?
No, that's a very good question. So typically we're looking at respirable as being the most dangerous of the three because it does get down to the alveolar region, which can impact the gas exchange. And so you want to uh, be more cautious if there are respirable particulates present in the workplace.
Okay, awesome. So I'm not seeing any more questions. Oh, sorry, Q&A has one.
There's one question from Michael in the chat too, if you want to grab that.
Thanks, I could do that. So, Michael, with budgets in mind for DRI sampling tools versus the capture sampling methods, how long are the devices typically reliable for?
That's a very good question about the DRIs. They are meant to be used for the full shift. Of course, if it's very cold, just like our phones or tablets, it's going to not last as long. So you really have to check with the manufacturer to find out how long those devices last for. But nowadays, with technology and the battery power, they should be good for the full shift.
Awesome, thank you. Great.
Okay.
Okay.
So if there are no more questions, we'll move on then. So the first of the hazards I'm going to talk about is silica. And silica is a common mineral that's found in soil, sand, and rocks. Quartz is the most common form of crystalline silica and most commonly used industrially. And silica is disrupted when there's grinding, cutting, drilling activities, and this creates respirable dust. And we talked about already that the respirable fraction is the most hazardous of all the three fractions. We're talking about 429,000 Canadians occupation exposed to silica, and the majority of these are male. In terms of mining, it is one of the top five industries where workers are exposed to silica. The International Agency for Research on Cancer, or IARC, has classified this as a known human carcinogen, or Group 1. Uh, and this is because of the long-standing association of crystalline silica exposure and the increased risk of lung cancer. Okay. Another disease is silicosis that could be caused by inhaling these crystalline silica particles. And then there's other diseases also associated with occupational silica exposure, such as pulmonary tuberculosis and COPD. In terms of sampling methods, there are a variety of different sampling methods available for sampling silica traditionally. So you can see on the left in the table here, you've got four NIOSH methods and one OSHA method. And the biggest difference here is essentially the type of analytical method that you would be employing. And this is important because you need to find a lab that can actually do that type of analysis. And so that is something that's very important. Not all labs are created equal. Not all labs have the same capacity. So if you are planning on sampling for any chemical contaminant, you really should find out if the lab is capable of doing the method that you have narrowed down to, or which is the one that you want to use. Because silica is a respirable particulate, you'll need what's known as size selective samplers. And so these are examples of size selective samplers. You've got cyclones, and then you've got what's known as a PPI. And these specifically look for the respirable fraction. Okay. So in terms of the sampling train for traditional hygiene sampling, you can see these are the different components. So you've got your pump, you've got your flexible tubing, you've got your sampling media, which is inside this filter cassette. And then you need what's known as a cyclone, as I mentioned earlier, and this allows you to collect the respirable fraction. And then the optional piece is this gold or yellow metal, which is the sample media cassette holder. And that allows you to put everything together. And there's also a clip at the very end, which I don't know if you can see. It's the end at the end of the black arrow. Then you can clip it to the worker's lapel. Okay. So I'm not going to show this video because this you can look at it anytime. But basically it tells you how to go about sampling for silica. There are some direct reading instruments out there as well. So I'm just provided some links for you where you can take a look at. So again, these direct reading instruments allow you to get near real-time measurements of the concentration of silica. Okay. So in terms of the occupational exposure limits, um, for your information, silica is actually one of the designated substances within Ontario. So if you have a designated substance like silica in the workplace, you not only have to follow Regulation 833, you also have to follow the designated substance regulation, which is Regulation 490. In terms of the exposure limit, in Ontario, it's currently 0.10 milligrams per cubic meter. And again, this is the respirable fraction, just to be clear. And so for those of you who don't know how to conceptualize the milligrams per cubic meter, it is a very difficult concept because a milligram is very small, and then a cubic meter is basically 1 meter by 1 meter by 1 meter. And so, which is the size of an appliance box, like something for your stove or for your washer or dryer. So that's about a 1 cubic meter. So I have tried to show it to you on this right-hand side, the image. So the light is showing you the dust there, approximately a milligram of dust, and then the green corners give you a sense of 1 cubic meter. So basically, a very, very small amount can lead to long-term health effects. And so that's why it's important to sample the air and in turn put in place control measures to reduce workers' exposure. In terms of the literature, I tried to look at Canadian papers first and foremost, and then also papers that had a larger number of samples as opposed to a case study, which is a very limited number of samples. So a very recent paper by Arundel et al. Looked at mining in Ontario, where they found the exposure levels for individuals range from 0.002 to 2.3 milligrams per cubic meter. Again, the reminder is that the OEL time-weighted average was 0.1 milligrams per cubic meter. And so a small fraction exceeded this. But then they also compared to other exposure limits that are found in other jurisdictions, which are more restrictive. So 0.05 for the OSHA permissible exposure limit, and that resulted in almost 15% of samples exceeding that value. And then an even more restrictive exposure limit is the ACGIH TLV of 0.025, and that was 31%. So basically, what they're saying here is that other jurisdictions believe that the exposure limit should be significantly lower than what is found in Ontario. Ontario hasn't changed it for a number of years, but these other agencies have reduced their exposure limit. So if we were to compare the exposure concentrations found, some of them already exceed Ontario, but they exceed a larger proportion exceed these more stringent exposure limits found in other jurisdictions. Okay. Another paper that was done in Alberta, and what they found was a geometric mean of 0.048 milligrams per cubic meter, which is potential overexposure because the Alberta exposure limit is 0.025 milligrams per cubic meter. So you can take a look at the references once you get a copy of the slide deck. I'm just going to skip the questions for the sake of time, and we'll move on to diesel particulate matter, or DPM. And so diesel particulate is a complex mixture of different gases and particulates due to the combustion of diesel fuel. It's estimated that approximately 897,000 Canadians are exposed to diesel engine exhaust at work. Just like silica, it is also classified as a group 1 carcinogenic to humans, according to IARC, because it is associated with lung cancer, and it may also cause bladder cancer as well. And it's estimated that about 6% of all annual lung cancer deaths are attributed to diesel engine exhaust exposure. The particulate matter of the diesel exhaust is of most concern, and particularly we're talking about elemental carbon. But there's also other stuff as well. There's organic compounds and metals. And then just like silica, we're mainly concerned about the respirable fraction here when it comes to this diesel engine particulate matter. Okay. Another video for you. This is a very long one, so you can take a look at your leisure. In terms of sampling for DPM, we are looking at elemental carbon as the best surrogate of particulate matter because it makes up the bulk of the emissions. And the one that they are suggesting is NIOSH 5040. Again, you have an air sampling pump, you have flexible tubing. The specific filter here is a quartz fiber filter, so it's very important when you select the sampling method, you know what filter is associated with that, because the different type of material that is used to make filters will have a certain affinity for the type of particulate. So in this case, you're talking about a quartz fiber filter. And because it's respirable, you'll need a size selective sampler. So this is just a image. You've seen it. It's basically the same as for the silica. The difference would be the type of filter that's used where DPM requires a quartz fiber filter. Okay. There are direct reading instruments available for detecting DPM. The thing is that they're non-specific. So that means that they will sample for all respirable particulates, whether or not it's DPM. So that's something that you have to think about, whether or not there's other sources of respirable particulates that could lead to a higher than expected exposure because it's not specific for just DPM. So three different examples that are commercially available for you to consider using to determine near real-time measurements of DPM. In terms of the occupational exposure limits, this is stipulated in another regulation, Regulation 854, mines and mining plants. The OELTWA is 0.12 milligrams per cubic meter for elemental carbon. And this is specifically for diesel-powered equipment that is operated in an underground mine. Okay, and this was a relatively recent development coming into play in September of 2023. So in terms of the exposure levels from the literature, this is courtesy of CAREX Canada, and they basically broke down the exposure to diesel particulate matter stratified by industry. And you can see here, I highlighted mining and quarrying, that there aren't that many individuals per se that are exposed. But what is important to note is that the proportion that is high, which is the deeper red or pink, you can see it's very it's a larger proportion relative to some of the other industries, meaning that DPM is there's a great chance of having high exposures of DPM in the mining and quarrying industries. In terms of the publications, I was unable to find anything specifically for Canada, so I found some other studies, one more recent in Spain and another one in Australia, which the first one in Australia showed that the elemental carbon exposure ranged from 0.01 to 1 milligrams per cubic meter, and that underground miners, not surprisingly, were exposed to higher levels of elemental carbon than those that were in above ground operations. And then the one in Spain, what they looked at was prior to implementing a novel control measure, they collected exposure assessments of individuals, and they found that there's a median concentration of 0.145 milligrams per cubic meter, with 90% of the samples exceeding the exposure limit set by the EU of 0.05 milligrams per cubic meter. So again, that kind of supports what was found in the previous slide, that overexposure is likely for miners. The references are here again. And then again, I just want to skip that and move on to the last of the three hazards, which is radon. Radon is naturally occurring radioactive gas when uranium decays. Okay, and so because it's radioactive, we're looking at a physical agent now. Again, energy that can cause harm. Radon is colorless, odorless, tasteless, and so when it decays, you're producing radiation. And again, just like the other two, it's classified as group 1 carcinogenic to humans, again, due to the well-established association with lung cancer. Okay, as we mentioned about the other hazards, inhalation is the most common route of exposure. And in terms of those people who are working in underground spaces, they often have elevated exposure to radon versus outdoor levels. We're looking at about 190,000 Canadians who are exposed to radon, and the greatest risk cohort are those workers who work in underground mines. And radon is actually the second leading cause of lung cancer in Canada. So what's important to note is that if the individual smokes and is exposed to radon, then the risk of developing lung cancer is significantly increased. Another quick video, so you can watch that at your leisure. And so I mentioned that radon is a physical agent, and I also told you early on that when it comes to physical agents and biological agents, the type of sampling method may not be as well established. And so this is what we're looking at here for radon. I'm going to show you a series of slides of different sampling possibilities in terms of what is found in this paper. That's a reference paper of all the different methods that are available for sampling for radon. So it's really up to you to decide which instrument A you can get a hold of, B is within your budget, and C meets your objective. So that's why I'm just going to give you a very quick overview of all the different types that are available according to this paper. Okay, so you can do long-term monitoring using alpha track detectors. You can do short-term monitoring using either charcoal canisters or this electric passive environmental radon monitor. Grab sampling we talked about, so you're collecting very quick samples to see if radon is present in the environment. Um, in terms of exposure modeling, you can use mathematical models or computer simulations to estimate radon exposure, but you need to have a variety of different information. This includes your ventilation rates, the different characteristics of the building, as well as work activities. So if you don't have that information or don't have knowledge of that, you will not be able to use these exposure models. There's dosimetry, so basically the worker is wearing a dosimeter to determine their exposure. You typically have to send these off to lab to get analyzed. They're not direct reading instruments per se. There's also real-time monitor, so this is where you set up the instrument to detect radon real time. And so the continuous alpha radon monitors is an example of that. And because radon may be found in indoor spaces, you might want to assess radon along with other common indoor air quality parameters such as carbon dioxide and VOCs. Okay. In terms of units to measure, just very quickly, becquerels per cubic meter or working level month. And on the bottom left here, you can see that there is a equivalency equation to compare those two units. Okay, I'm just looking at the time, so I just want to make sure there's time for Q&A. So I will wrap it up very shortly. In terms of the exposure limits, again, you're looking at Regulation 854, mines and mining plants. Because it's radiation, it's a linear no threshold model from a toxicological perspective. So they're basically saying that any exposure to radiation can result in a health effect. The more you're exposed, the greater your chances of developing health effects. As a result of that, what they want to do is to ask employers to reduce the levels to as low as practical possible, or a LARP, as low as reasonably practicable, is the precautionary principle that we strive for. Okay. If, depending on the concentrations that you measure, you have to do routine testing. So if you find radon greater than 0.1 WL, you have to test at least monthly. If you find it between 0.06 and 0.1 WL, you test quarterly. And if it's less than 0.06, you test that at least once a year. Okay. So in terms of literature, there is some papers done in Ontario and in Canada. And so the paper by Zhang et al. Found a mean value of 7.5, but there's a great variability in that. You can see by the standard deviation being almost 25. And then the group that had the highest cumulative exposures were uranium miners, and then followed by only uranium miners or only underground miners. Okay. And then in terms of annual radon exposure in the paper by Chen, you can see that those individuals who work in underground mines have much greater exposure than those individuals that work in surface mines. Okay. So again, the references. And the last thing I want to talk about are exposure judgment tools. And the reason why I want to bring this up is that for those of you who have some experience doing air sampling, you know that you're limited by resources in terms of time and money. So sometimes you cannot sample collect as many samples as you would like. So using exposure judgment tools can help you in that regard in the sense that when you have limited number of samples, you can input your concentration into these online tools to help you make a judgment in terms of the acceptability of that exposure. Okay. And so the other benefit of these tools is that it takes out the subjectivity of that. And because the data is generated by the tool and it models it based on all these different parameters. Okay. You do have to be familiar with the tool as well as making sure that the quality of your results, meaning the stuff you get from the lab or your direct reading instruments, are good quality data. There are different tools out there. IH stats and Expo stats are probably two of the more common ones. And then if you take additional courses, which are free and available online, you can then become registered as an exposure decision analysis. And so I took this a few years ago, and which allows me to say that these tools are I know how to use the tools and know how to interpret that monitoring data. So. And I just want to explain to you why I feel that this is important for those people who might want to consider using those tools is because they provide outputs that are easy to understand. So it's known as a traffic light. So you got the red, green, and yellow. And so depending on your exposures, you can determine whether or not it's acceptable or unacceptable. And then you have the corresponding color bar charts to tell you about the acceptability. So on the left-hand side, you have the sample result of 0.7 ppm, and you can see that there's a lot of green, meaning that the exposure is considered acceptable, and you don't really have to follow up in this situation. In the middle panel, you've got a result of 20 ppm. In this case, you've got a yellow of 36.3 and a red of 38.7. We know yellow means caution, red means stop. So therefore, in this case, we are uncertain or it's possibly unacceptable, and therefore we really should take a look at this further. And then on the right-hand side, you have an exposure result at 70 ppm, and you can see that 86% likelihood of being red. So therefore, we have a very good feeling that this is likely unacceptable, and therefore we do have to pay attention and prioritize these particular individuals that are exposed to this concentration. Okay. So some additional resources for you that are related to occupational hygiene and or mining. And thank you very much for taking the time to listen to my discussion. Hopefully you found it informative. If you want to reach out to me, my email is at the top there. And if you want to see additional information, I have put up my academic website there as well as my LinkedIn profile. So thank you very much. I really appreciate it.
Awesome. Thank you, Dr. Han. We do have a couple of questions here in the Q&A. So one is there's a focus on radon, yet thoron may also pose a risk. Should both radon and thoron be measured?
I'm not very familiar with thoron, to be perfectly honest, but radon has been certainly around for a while, and thoron hasn't been as well researched, so I really can't speak to that.
That's okay. Perfect.
Sure.
So more holistically, is there any method of determining the synergistic effects of these exposures of all chemical agents? Are there those kinds of methods? Are we leaning towards doing that?
Yeah, that's a very good question. So if you, and it's a very good point that you're typically exposed to multiple chemicals or multiple hazards at the same time. So there is an additive model in occupational hygiene and the regulations where if you know the exposure level, exposure concentration and the exposure level, you do a ratio. So it's C1 over L1. C1 is concentration of the first hazard over L1, which is the corresponding exposure limit, plus C2 over L2 plus C3 over L3. And if that ratio is greater than 1, then the risk is potentially considered unacceptable. So let's just say that your concentrations and your exposure levels, so your concentration exposure to a certain chemical is less than its corresponding exposure limit, but in combination with these other hazards, collectively, they may sum greater than one, and therefore that is considered unacceptable.
Okay, awesome. So there's probably something to combine all these effects. Okay, great.
Yes, yeah.
And do you have any experience? I know you talked about a little bit about ventilation and things like this, but where do you from the readings, where are the biggest gaps in our hierarchy of controls for in our current approach to these types of hazards?
That's a very good question. As you know, a lot of workplaces simply give people personal protective equipment, and so they think it is the quickest and simplest way for obvious reasons. However, according to hierarchy controls, you should start with the most effective, which is elimination and substitution. For the most part, elimination substitution is not likely, because you have to work in an underground mine. The mine has the silica, that has the radon, and has the DPM with the the trucks and other transport vehicles. So that might be a bit challenging. So you're left with ventilation. And so I know the underground mines, they do have the ventilation. Having said that, is it tested regularly? Is it maintained properly? Those are challenges that I think haven't really been examined. They might be designed properly and installed, but that other piece of the maintenance and the inspection, I'm not sure if that's really been done properly. If I also understand it correctly, a lot of these diesel trucks are being phased out with electrical vehicles, so that would help in that regard. So that's a form of substitution.
Awesome. Another question here. Are there any tips you could provide to students that are just getting into the industrial hygiene field? So we do have a few here.
Um, Tips? Well, I mean, certainly going to some of the sources I have provided for you in this presentation, you can learn a bit more. If you want to get education, there are a variety of different courses available to you in terms of learning a bit more about occupational hygiene. And I would also suggest that as a student, you consider joining a variety of different professional associations, the Occupational Hygiene Association of Ontario, which I believe Dr. Goggins you presented at last fall. That's an association where you can be mentored with a more seasoned professional to learn a bit more about occupational hygiene if you choose to do so. And then there's also other groups like the American Industrial Hygiene Association, or AIHA. They have student sections or student memberships, sorry, that you can certainly subscribe to get some more information from them.
Awesome. There's two more questions. I think we have just a little bit of time and then we're going to take a break. So, do
Oh,
the tools you use for radon measurement give you results for radon progeny? If not, what sources are there for radon progeny or daughters measurement?
that's a very good question, and unfortunately, I can't answer that. I didn't have a chance to go through exactly what those tools measure, but the paper I provided should explain that for you. So I do apologize for not knowing that answer, but that paper should provide that for you in terms of what exactly those devices are measuring.
No, no, that's okay. Perfect.
Yeah.
Yeah. And so, are there any disadvantages to using PPIs instead of cyclones despite the ease of use?
That's a good question. To my knowledge, I don't know if there's a paper that has evaluated PPIs in terms of comparison to the gold standard of cyclones. The beauty of it is that it is much easier to use. I'm not sure if it's recognized as a method per se because I presented to you all the ones for silica and they're all still traditional with using the filters. PPI, you don't have to worry about using the size selective sampler. It already is built into that. So ease of use, great. Whether it's as effective and accurate as the standard, I'm not 100% sure about that.
Okay, great. Well, thank you, and everybody, thank you for your talk today. We really appreciate all the information.